Hi everyone! In the next two sections, we will be diving into an introduction of the battery management systems. We will be defining what the BMS does and exploring its key features, as well as we will give a look at the different structures and configurations of the BMS. So let's start with the definition. And as you may know, the BMS is a vital component in any battery pack. The primary role of the BMS is to monitor, to control, and to protect the battery, and mostly to ensure both the safety and efficiency of the full battery system. Without the BMS, the battery and even the end user will be exposed to the risk from issues like overcharging, over-discharging, short circuit, or eventually even overheating of the battery cells. Later in this course, we will explain in depth how the BMS reacts to protect the system in each of these conditions. Here we will look at what are the general functions and features of it. So as was mentioned, the BMS has the main responsibility of keeping the battery within the safe operating area all of the time. In general, we can say that the BMS will have four main features. The first one is monitoring that the battery condition by continuously tracking critical parameters such as the voltage, the current, and the temperature. Also, the BMS will be controlling the battery operation, ensuring that it will stay within the safe limits and efficiently manage the energy flow in the system. It will be doing all the battery estimations that are going to be essential for the performance or for knowing how the battery is performing. Some of the parameters that the battery estimates are the state of charge and the state of health that also help us to know the lifespan of our battery. And finally, all the communications with external circuits, ensuring that the system and the battery is smoothly integrated into all the devices and applications that are connected to it. So let's see what are the subsystems and how the structure of a BMS looks. So here we have a very general diagram of what a BMS might include. This, of course, will change in every design, but these are the very high-level features that the BMS includes. So we have a control system that has the switching components that help us to connect and disconnect the battery from the loads, as well as the balancing system that will be that ensures that all of the cells are being operating at the same state of charge. Then we have the monitoring and diagnostic system that is connected to all the measurements of voltage, temperature, and current. And also there is this block that includes all the data analysis and processing, as well as communication with external elements. We will describe each of these subsystems in detail in the next slides, starting by the monitoring and diagnostic subsystem. This subsystem, as was mentioned, is responsible for the measurement of all of the critical parameters like the voltage, temperature, and current. And basically, it continuously collects and analyzes the data in that way that it can ensure that the battery is operating within the safe limits. Some of the sensors that this system have, for instance, is the cell voltage. All of the cell voltage are being measured to detect overvoltage or undervoltage conditions. Also, the cell's temperatures are measured to monitor any overheating or any thermal irregularity that the battery pack may have. We also have measurements of the pack voltage and pack current to ensure the overall system operation, and as well insulation measurements. So we have insulation resistance measurements to detect failures in the electrical insulation system. The core features of the BMS and the monitoring and diagnostic subsystem is the integration of all of these sensors that will ensure accurate readings of the current status of the battery. On top of that, it will have real-time detection of anomalies that will help us to identify potential issues that may arise and that we can detect early on to react in a preventive manner. All of the data that is being measured here is collected, and this will allow the battery to perform diagnostics and to prevent any undetected system faults in such a way that the system can react. Without having this accurate monitoring and without having or with having faults that will go unnoticed, we will be leading to catastrophic failures or significant reductions in the battery performance and lifetime. So this system in general is crucial for a safe and a reliable operation of the whole system. Then it wouldn't be possible only monitoring. We also need to take actions based on those measurements. And the next subsystem is the control and protection. This subsystem has the function to enforce the operational limits and protect the battery against any detected condition. It manages all the switching components, for instance, the contactors and the relays that are connected between the battery and the loads, with the purpose of disconnect the battery in case of any unsafe conditions. It also will manage the energy flow from the battery to the loads, and also manage, for instance, the cell balancing to maintain the uniform state of charge across the whole battery pack. Between the core features of this, we have that one of the most important is that it activates emergency disconnects during unsafe operation. In any of these cases, short circuit, overload, overcharging, overheating, the battery is completely isolated from the system to prevent any damage. Also, it has dynamic control of the flow of power and the usage of the energy, as well as mentioned, the balancing of it. Finally, we have the subsystem that is in charge of the analysis and the communications. This subsystem will process all the data that has been collected by the monitoring subsystems, and it uses to estimate the battery parameters and to facilitate the system integration. So some of the core functionalities of this subsystem is the estimation of the state of charge, the estimation of the state of health, as well as the communication of these parameters and all of the rest of parameters that are being calculated in the battery with any external subsystems, using some protocols that are very standard in the industry, for instance, CAN, LIN, or Ethernet. In the core features, we have very advanced algorithms that ensure precise estimation of these parameters, and those precise estimations is what allow us to optimize the performance of the battery and, for instance, to be able to extend its lifetime. Also, it is very important for this subsystem to have robust communications with the systems, and this is important to coordinate the operation and to be sure that the data is being shared in a correct way and that there is enough reliability on those parameters that are being shared. That mentioned that then we can see how all of these features are integrated into the systems and what are the different architectural approaches or the topologies that are being used in the different applications. When we refer to the topology, we are talking about how the system is going to be structured and how the system is organized to manage the overall battery pack. Depending on the size of the battery, depending on the complexity and the application, the BMS can be designed using these three main topologies. We have first centralized topology, where all of the batteries are managed by a single central unit, as you can see over here. Then we also have modular topologies. In this case, the battery pack is split into modules, and each of the modules has its own BMS that will be acting individually, independently. And then we have master-slave configuration that I would say that is a middle point between the centralized and a modular, and basically it combines a central control unit, that is the master BMS, with distributed slaves that will handle, for instance, the modules. Each topology has its advantages and disadvantages, are their use in different applications. We will explore in the following slides what are those advantages and when to use each of those. So let's start with the centralized topology. As was mentioned, the BMS in this case consists on a single unit that will manage and monitor all of the battery cells and all of the modules. This means that all of the sensors for voltage, current, temperature, and so on are going to be connected directly to this central unit, and this, for instance, will allow us to have synchronization of all of the data and synchronization between the data that we are being acquired and the control strategies that then we are applied. Some of the advantages of this topology. So when we only have one central control unit, the complexity of the whole system is reduced. This makes the design process simpler, cheaper, and also straightforward. In addition to that, as we have fewer components, it means that we also have less circuitry, and as a consequence, there is a lower material cost and production cost of this kind of topologies. All of the data of the battery pack will go to a single point where everything is being processed and everything is being analyzed. This simplifies all the diagnostics and the control logic that the BMS may have. And in addition, as we only have one single element to inspect, the maintenance and the troubleshooting, it's easier in this topology. However, there are some disadvantages related to that. So one of the disadvantages is that there is a single point of failure. If the central BMS fails, the entire battery system is at risk of failure. The complexity in the wiring when we have large scales will grow, and this at the end will become a spaghetti mess of all of the cables going to one single circuit. Also, adding more cells and more modules become challenging as the system grows, since at some point it's going to be unsuitable to have this kind of operation. Having said so, the most common use cases for these topologies are very simple and small battery systems that only have few cells count. I will say that a battery system with voltages below 80 volts, and those are applications such as, for instance, 2- and 3-wheelers, light electric vehicles, e-scooters, small medical applications, and so on. Then we have the modular topology. This design will offer a little bit more of flexibility and scalability for larger battery modules and for systems that are a little bit more complex. In this design, the battery is divided into several modules, and each of those modules has its own dedicated BMS and independent BMS. These module level operate independent, but they work together to form a complete entire battery pack. Some of the advantages is, for instance, that the modular design will allow us to easily expand or reduce the battery system by simply adding or removing some of these modules that already integrate the BMS. This makes them suitable for applications where the battery size might change over time, for instance, in grid energy storage or backup power systems where we want to scale up or down based on the final user. requirements, it makes sense to have this kind of topologies. Also, another advantage is that it has a better tolerance to faults than, for instance, the centralized architecture, because in this case, if one of the modules BMS fails, the rest of the system can continue functioning. And this is going to be very important, for instance, to continue monitoring and communicating with the rest of the system to inform of any failure. It also has as another advantage that the wiring is simplified. The length of these wirings that are sending signals for voltage and temperature are going to be shortened, and the connections then will reduce the complexity and facilitate the assembly of the whole system. The disadvantages is, of course, that it will have a higher cost. Each module will require an own BMS, and basically this means higher components, higher bill of materials, and more steps in the assembly process. The autonomy of each of these models, although it is on the one side what allows this topology to be more flexible, on the other side it might complicate certain specific processes of the battery, for instance the balancing of the cells. In a battery, all of the cells need to have the same state of charge and to be discharged and charged at the same time to guarantee that we are taking most or that we can take as much energy as possible, and that also that the battery will be working safely if we do it in that way. So to be able to know that all of the cells have the same state of charge, even if they are in different modules, at the end we need to have a robust communication system between these BMS, between this modular BMS, and that increases a little bit the complexity in the coordination of those parameters, who is handling what, and what are the responsibilities and how they are acting as a group. Usually then this topology is used in applications like energy storage systems, where the batteries need to be scaled to meet the demand, and in some industrial equipment where the battery pack is composed of many modules, it also makes sense. There are also some EVs that might use this architecture, but I will say that the master-slave architecture is more common in electric vehicles. This is then the master-slave architecture, the final, or the topology, the final of the ones that we will revisit. This is a distributed architecture designed for very large and complex battery systems. In this configuration, as you can see, we have a central master unit, and this central master unit will be controlling the overall battery system. It will have communications with multiple slave units that are this one over here, and these slave units will be handling localized monitoring and control of the individual cells of those modules. The master unit will collect the data from all of the slave units, they will process it, and they will coordinate the full system operation. Some of the advantages that has this system is that is very, as well as with the modular approach, is scalable. So if we want to add new modules, it's gonna be relatively easy to include it, and it makes it very interesting for large battery packs, and battery packs that have high capacity applications, for instance, that are using high capacity applications. Also, the distributed monitoring is very interesting. Each slave unit manages a small section of the battery pack. This reduces the computational, the load of the resources, the computational load, and the processes that are being taking place is split and ensures localized control of those. The centralized control It's also an advantage because it provides a single point for the system to take decisions, to communicate with other subsystems. It has the data aggregation and the management of all of it. So it is very important, and also it provides a good reliability. So to have these distributed slave units can enhance the fault detection and the insulation, as well as allows granular monitoring of the whole system. On the other side, this is the most expensive architecture, since multiple slides units needs to be procured, as well as one heavy computational resources BMS. The complexity is also very high, and I would say the communications and how all of that is managed, to be sure that the signals that we are acquiring and the data that we are monitoring are synchronized, is also critical for this system. That means that it will rely heavily on the protocols that we will be using to communicate between slaves with the BMS, and also the BMS with external parameters. Some of the things that we have to think in this kind of architecture is, for instance, the redundancy. How do we guarantee that in case one of the measurements or one of the communication channels is broken, we can still have communication within the whole battery systems. This is mostly used in large-scale energy storage systems or in electric vehicles, especially with current buses that has a high capacity and that requires high reliable battery systems. Also, this kind of architecture that is the more complex, but the one that has most of the system advantages, it can be used in aerospace applications as well, because it's very robust, and that is critical in those kind of applications. Finally, let's summarize and let's compare the three topologies that we have studied to highlight what are the key characteristics of each of those. So as we look at it, first we have the centralized topology, that is the one that has in the design complexity is the most simplified system, and the one that since it only has a single unit that controls everything, also is the one that is the cheapest, so that's another advantage. However, the flexibility and the scalability is limited. Because of that, it is more suitable for small systems. On the other side, we have the modular topology that is very flexible. I will say that in the cost is it's in the middle between centralized and master-slave. It's not as cheap as the centralized, but not as expensive as the master-slave configuration. And it is in safety, I guess it provides good safety, since failures in one module does not affect the entire system. And finally, we have the master-slave. In this case, as you can see, it is the one that has the highest cost. It is also the one that offers a very good flexibility, and the biggest advantage of it is the safety that it has, since the master unit is a single point of failure, but also you have the localized monitoring that helps to mitigate all those risks. So it is very interesting. In this case, the master-slave topology is very good in complex applications, like, for instance, the electric vehicles.